Hey guys, I'm Aryan Agarwala. I'm 6 stars in CodeChef and Master on Code Forces. Welcome to our channel, Learn Competitive Programming with CodeChef. Every week we upload tons of competitive programming content. So here's a reminder to subscribe and click on the bell icon to stay notified. Today we're going to discuss a problem named dense graph. This problem I think is around easy medium. It's maybe more towards the medium side for some people. This appeared in the March Long challenge for 2021. The prerequisites for this problem are merge sort tree, breadth first search, and basic C++ STL sets. Now, merge sort tree, we're actually going to use a variation of which is implemented via sets. Um, but if you know basic merge sort tree, then you should be able to pick up the one with sets pretty fast. So yeah, if you know these three topics, you should be fine for this tutorial. If not, then you should go learn them now and then come back. Okay. Yeah, so let's read the problem statement. The problem states you're given an unweighted directed graph with n vertices numbered 1 through n, and you're also given two m ranges. So the ranges are a1 b1 all the way to am bm, and then c1 d1 all the way to cm dm. These ranges describe the edges of the graph in the following way. For each I in 1 to m, and for each pair of vertices u in aibi and v in cidi, there is an edge from u to v. So basically, we have like pairs of ranges AI, BI, and similarly CIDI. Okay, and there are like pairwise directed edges between the nodes in AI, BI to the nodes in CIDI. Okay, now we're given two vertices x and y, and we want to find the shortest distance from x to y, or determine that there's no path between x and y, or from x to y rather. So the input format is pretty standard. Um, so we output either the shortest path or -1 if there is no path. And the constraints are the test cases are less. So the multi-test format, test cases are between 1 and 10 to the power 5, and the number of nodes is very high. It's 10 to the power 9. So that's something to keep in mind. M is between 1 and 10 to the power 5. XY is yeah fine. Um, AIBI is again standard constraints less than n, and the sum of m over all cases does not exceed 2 into 10 to the 5, which is also expected. Okay, so we're looking at some kind of solution dependent on m, maybe order of m, order of log m log m, order of m log square m, something along those lines. Okay, now let's look at a sample case. Yeah, uh, so we have this sample case 5212, and we have this set of edges. So why don't we draw this out? Sorry. Yeah. So we have five nodes, right? One, two, three, four, and five. Now let's look at the edges presented in the problem. So the first range is AIBI is 1, 2, and CIDI is 4, 5. Okay. So 1, 2, and 4, 5. So that means there's an edge from 1 to 4, 1 to 5, and similarly 2 to 4, and 2 to 5. And these are directed, so let's add the arrows. Okay. And then we have AIBI is 5 to 5, and 2 and 3 is CIDI. So yeah, so there's an edge from 5 to 2 and 5 to 3. Okay, and we want to find the shortest path from 1 to 2 in this graph. So it's pretty clear that the shortest path in this graph from 1 to 2 is 1 to 5, and then 5 to 2. Okay, and so if you want to compare with the test case, what we're doing is in this first range, 1 is on the on the outgoing side and 5 is on the incoming side. So you go from 1 to 5 via this, and then in the second set of edges, 5 is on the outgoing side and 2 is kind of on the incoming side. So we go from 5 to 2 via this, okay? So the path is of length 2, and we can verify that it's the shortest path because there's no path directly connecting 1 and 2, right? So we can conclude that the shortest path is of length 2, which is exactly what's given. Now, the second case is similarly 5 nodes, um, sorry, 6 nodes, I'm sorry. And so I won't actually draw this out because it's quite easy to see, but we want to pass from 3 to 4. However, there's simply no incoming edge to 4, so there's no way there can be a path, right? Okay, so in this problem, we're basically being asked to find the shortest path on an unweighted graph. Now this immediately leads us to BFS. Okay, so we're gonna have to work with the internal workings of BFS a bit. So let's quickly get that done. Okay, let's just describe it once. So we have a node X where we start with. Okay, so we push X into a queue. Okay, and we say distance of X is equal to 0 and visited of X is equal to true. Okay, then we say while queue is not empty, we'll say int cur is equal to q dot front, and we'll pop this. And then we'll go over the edges of q. Not q, sorry, of cur. And we'll say that if we have not visited E, then we'll q dot push E and visited of E is equal to true. Okay. Also we set distance of E is equal to distance of X plus 1. Yeah. So this is a standard BFS. Now, what's the issue with applying this naively to the graph we have? Well, the issue is that this runs in order of V plus E, and on the graph we have V is equal to N is equal to 10 power 9, which is already too large, but to top it off, E is equal to N squared is equal to 10 power 18. So this is way too large to run. Okay, so we need to make some optimizations here. Now, I'm going to describe a quick optimization first. Okay, so let's say we're exploring a range CD. Okay, so we're on some node X in AB. Okay, and we're exploring all of the edges from X to this entire range CD. Okay, so there's a lot of inefficiencies here. Okay, and to give you an idea, I'm going to give you a practical example. So let's say we have AB is like 1 to 10 and CD is 11 to 20, and then the next AB is 11 to 20, and the next CD is 21 to 30, and let's say X is equal to 1. So what happens? We go from 1 to 11, 1 to 12, 1 to 13, all the way to 1 to 20. Then we go from 11 to 21, 11 to 22, all the way to 11 to 30. Then 12 to 21, 12 to 22, all the way to 12 to 30. So on and so forth until you do this with 20, 20 to 21, 20 to 20, all the way to 20 to 30. And note that even though you don't actually end up revisiting those nodes between 21 to 30, you do actually make those iterations, and then you just stop yourself from revisiting them by checking the visited array. Okay, So these are iterations done, okay, and they are costly. We just like so for example, this can have size like n by 2, and this can have size n by 2, and so even on just cancelling the visits, we've made n squared. Okay, so but the important thing to note is that there are actually a ton of wasted iterations here, because the reason is that 11 and 20, this range 11 to 20, have literally the same edges, right? So why would we bother visiting 12, 13, both, when it's just the same as to visit one of them, right? So now, to eliminate this inefficiency, I say let's only visit nodes which are the upper bound of at least one range. Okay. So for example, in this it would be, let's call this the set S is equal to, in this case it would be 10, 20, 30, but it's actually equal to the set of all B's and D's, okay, over all ranges. Okay, and now so in this range 11 to 20, we'll only, to make this a little more explanatory, why would I replace this 20 with 15? Okay, and so we'll add 15 to this set. Okay, now so what I'm proposing is that while visiting this range 11 to 20, instead of pushing 11, 12, 13, 14, everything all the way to 20, we actually just push 15 and 20. Okay, and why does this work? Well, the reason is that all these nodes in the middle, 11, 12, 13, 14, they will have the exact same nodes as 15, right? Because if they didn't, then it would mean that there's a break in the partition earlier. So one of these things would have to be an upper bound as well, okay? Right. And now, similarly with 20, right? 16, 17, 18, so on and so forth, always have the same nodes as same edges as 20. Okay? So this is the idea, okay? And this actually helps us a lot, because this means that, number one, since we store these in a set, we can just do some kind of binary search on a set to retrieve, which I'll go into later, but we can do a binary search on the set to basically retrieve the next node we want to visit, okay, the next upper bound we want to visit, and by erasing them from the set right as soon as we get them, we actually don't waste any time at all on the case that we go to a visited node. Okay, and the number of nodes we visit again is bounded by the number of ranges, right? Because we only push B and D, so it's 2 into the number of ranges. Okay, and the number of ranges is equal to it's equal to 10 power 5, okay, or 2 into 10 power 5, whatever. So basically 2 into m. Okay, so we have 4m, not 4m, I'm really sorry, we have 2m, the size of the set is 2m, okay. So we basically end up visiting 2m nodes, okay, in this entire area, okay. And we don't, the most important part is we don't waste single iteration on the case that we've already visited this node. So this is a dramatic improvement, okay, because this order of, so this becomes order of m, okay, and the thing is this order of m is not local to this particular iteration. This order of m is the summation over all iterations, okay, so this is the total thing. And of course there are going to be some log factors here and there, but we'll account for that later, okay. Now, the more pressing issue is that how do we actually generate these ranges CD that we're going through, right? Like if we're at a node X, then somehow we need to find all of the AI BI such that AI is less than equal to X is less than equal to BI, and then we need to explore the corresponding CIDI. And though this might seem simple, this is actually a pretty complicated task to do fast, okay. So what we're going to do for this is merge sort tree. But this time with a set, okay. So the idea is that we keep all of these tuples a, b, c, d into a vector v, okay, and we simply sort this vector, okay, according to a. So we have v1, v2 all the way to vm, such that a1 is less than equal to a2 is less than equal to dot 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 less than equal to am. Alright. Now we want to find the largest I so that ai is less than equal to x, okay, and this is simply done via binary search, okay. And then after this we want to find the set of j such that 1 is less than equal to j is less than equal to I, and bj is greater than equal to x, okay, because these two combined will fulfill the condition we mentioned earlier, right? It will fulfill I'm not sure, whatever, it will fulfill the condition that a is less than equal to x is less than equal to b, okay. I think I wrote it up here, yeah, this condition, okay. So how do we find these b I mean the set of j's, okay? So what we do is a very simple way is to basically push all of this stuff into a merge sort tree, okay. So at the base level we'll say that seg of I representing the range xx contains, it's a vector which contains only the tuple bx cx dx, and this order x is basically what we sorted v in, okay. It's basically the same order, okay. So we create this merge sort tree with sets, and we build the entire thing, no problem, something like m log m, really not an issue, okay. And then all we have to do to so what we'll do is we won't actually generate this entire set of j together, okay. All we'll do is we'll just in one query we'll take any one random element from this set, okay, and we'll do this again and again until we've exhausted all of the elements in the set, okay. It's essentially the same thing. So all we have to do is every time we do a regular merge sort tree query, and every time we're at an endpoint ab which is inside the range we're looking for, so basically ab so a is greater than equal to 1 and b is less than equal to I, okay, and ab might be misleading because there's no connection between this ab, okay. Ab is just a random range which is represented by this node. So whenever we reach a terminal node ab, then we basically just binary search for the first tuple which is bigger than cur 0 0, and because we compare element wise, it will be that bx is also greater than equal to cur, okay. So now the segment tree will return us something, and you can take min max whatever you want to merge over two children, but eventually what we'll have is that the segment tree will return us some bx cx dx so that ax is less than equal to cur is less than equal to bx, okay. So meaning cur has an edge to every node in the range cx to dx. So after we have this range, we can handle it like we discussed earlier using the upper bounds and the binary search and whatnot. And then once we're done handling this range, we can simply delete it from our merge sort tree, okay. So it will never be revisited. So this entire thing becomes something like order of m log square m because that's what the updates and queries will be in the merge sort tree, okay. Yeah, so that's what we get. So you get what we're doing, we're basically visiting each range once and then removing it from from our merge sort tree permanently, and then inside each range we're visiting the each upper bound once, and then we're removing that from the set of upper bounds itself, so that our total comes out to something like order of m log square m. Okay, and this is enough to pass. So let me just show you the code. Yeah, so we have this code. So we just start by taking the number of test cases and we iterate down. We take an nmxy, we go from 0 to m, input abcd, we push it into this vector v. Okay, then this high is basically the set s that I discussed in the over here. It's basically the set of upper bounds. Okay, here. So okay, we sort all of the v's so that it's in ascending order of a. The first thing we do is that if x is equal to y, we simply output 0 and we continue to the next test case, right? If they're the same node, then I mean it won't have any difference between it, right? So we can just output 0. Our program might be able to handle this, but it's really no use in testing it. So I've just done this beforehand. Now I'll show you all of the other functions we're using once. Yeah. So this getInt function, what we're basically doing is that in the vector v we discussed, which contains tuples of the form a, b, c, d, we take in an input x and we return the first tuple, the last tuple in which a is less than equal to x. Okay, we return the index of that last tuple. Okay, which is tr, and if no such tuple exists, then we return -1. Okay. Now next, so next is a function on our set S of upper bounds. Okay, so we basically just do a lower bound on this set, okay, to find the smallest k in S such that k is greater than equal to x and k is an upper bound. Okay, if no such k exists, then we simply return 1e9 plus 5. Otherwise, we do star it, right? Now we come to our segment tree functions, our merge sort tree function. Sorry. So again, in a merge sort tree, when we reach the terminal point where L is equal to U, we simply insert this tuple of form B, C, D, and we return. Then if this is not the case, then we recursively build the left and the right side, and then we merge it together by just doing a iteration standard. It's like, this is basically just merge sort tree with an extra log factor. Now for queries, it's the exact queries are described in the on the whiteboard. So basically, a query LUI is just the parameters of a segment tree search, and XY are the special parameters. Okay, so what we're doing is in the range 0 to X, we're finding the first BCD such that BCD is greater than or equal to Y00. Okay, the only important condition being that B is greater than or equal to Y. Okay, so we do a low bound on this. If it is equal to segi.end, then it indicates that nothing exists. So we return something called IV, which is an identity value, and it's important. So it's defined as 10 to the power 9 plus 5, 0, 0. Okay. Otherwise, if something exists, then we just return what exists at that location. Okay. Now, obviously, if the query is out of range, we just return the identity value. Otherwise, we're taking min over both of the children's results. And note that IV gives a very high value, so the min will always prefer a value if you found one. Okay, like if you found a real value, it will be preferred over IV. Okay. Then we have the update function of the segment tree. So the observation used here is that if X exists in some node in the segment tree, then it'll be part of all of its ancestors as well, right? So when we're removing X from the segment tree, then what we're doing is we're basically checking if X even exists in this on this node. If it doesn't exist, then it doesn't exist in the subtree either, right? So we just exit. Otherwise, we first remove it from this node and then we do it recursively for the subtree. Okay. This resec function basically just resets the entire segment tree, clears all the sets, and this refresh function clears the global variables v and high. Okay. Now back to our BFS. So we push X with distance 0 into the BFS queue, and we erase X from the set of upper bounds if it exists in the first place. Now we go into our BFS, we find the current node, we get the current distance, and we remove it from the queue. Okay. Then we get the index we wanted from this getInt function. Okay. So up till this index, all of the a's are less than equal to our current node. Okay. If index is less than equal to -1, then there is no such index, and we just continue. Okay. Otherwise, we take this tuple of form BCD as a query in the range 0 to int. Okay, and we're basically finding all of those tuples which have b greater than equal to cur node. Okay, so that basically make sure that cur node lies in the range AB, so that cur node has then edges to the CD. Okay. Now, while this dest is not equal to the identity value, basically meaning that while dest is not equal to while dest still exists still. Okay, so while a next edge still exists, or rather a next edge range still exists, we keep on going forward. Okay. Now this could actually be a slightly written a different way, which could help. So let me do that. Yeah. So the first thing we do is that if second or first is basically C. Okay. So if C is less than equal to y and y is less than equal to d, then immediately we have an edge to y, right, which is what we want, and the distance will be cur is +1. So we just output that and we go to the next test case. Okay. Otherwise, we take cur to be the first upper bound in the set of upper bounds, which is greater than equal to C. Okay. And while this cur is less than equal to d, we like erase this cur from the set S, we push it into the queue, and then we update cur to find the next bigger upper bound. Okay. Then we update our merge sort tree by completely removing this tuple BC that we had gotten from it. Okay. And then we update dest to be the next smallest BCD which exists, so that b is greater than equal to cur node in that range. Okay. So this is our entire this is the entire part of visiting new nodes. Okay, this is like where really the entire trick of the problem lies. Okay, and now if we still haven't visited y, then it means that there's no paths to y, so we just output -1 and we move on to the next test case. Okay, and I've already submitted this and run it like a few minutes ago. So yeah, we got an AC. Okay, and yeah, it's the same code, you guys just verify if you want. Okay, so yeah.